So thanks for the organizer. My report is a well-balanced central-upwind scheme for the thermo-rotating shallow water equations. And this is a joint work with Professor Koganov and Professor Zetlin. Okay, this is the outline. I will first briefly introduce the one-dimensional thermo-rotating shallow water equations. And then I will mainly introduce the proposed well-balanced semi-discrete central-upwind scheme. And after this, I will show you some numerical examples to verify the proposed numerical schemes, and then some short conclusions. Okay, let's begin with the one-dimensional thermo-rotating shallow water equations. So in the equation, we have in the study system, we have four equations. The first one is the mass conservation, and the second and the third one is the momentum equation. And if we look at the first three equations, we can find that it's our rotating shallow water equations. And here, if we consider the horizontal gradients of the temperature or density, we will obtain the additional fourth equations. It's an equation for the buoyancy. So it's our thermal version of rotating shallow water equations. And here, F is the Coriolis force. So in applications, we can use this system to model the atmospheric or density temperature gradients. And recently, we developed the two-dimensional numerical schemes. And the two-dimensional numerical schemes is much more realistic because we can use it to study the propagation of vortex and study the dynamical physics. But here today, in this talk, I would like to talk about the development of the numerical methods for this one-dimensional system. And before I introduce the numerical scheme, I would like to point out the steady-state solutions of the study system. Because as we know, the steady-state solutions is very important, and many relevant solutions can be viewed as a small perturbation of the steady-state solution. So what's the steady-state solutions of this system? And we look at the second equation. If we set P is equal to 0, it means that if V is equal to 0, then in the third equation, is this space derivative can balance the right-hand side. Then we have the steady-state solutions. So it's our steady-state solution. V is 0, and this space derivative balance the right-hand side. So, and many numerical methods are developed to preserve these steady-state solutions at a discretized level. And also, we want to develop such numerical schemes. And to this end, we first introduce a global equilibrium variable L, and the L is given by this equation. Here, R is a space integration of the right-hand side in the third equation. And when we use this global equilibrium variable L, we can rewrite the studied system into the following form. So our steady-state solutions will become P is equal to 0, and the L is a constant. So we want to develop numerical schemes which can preserve this steady state. And here we have a more professional name. It's a thermodystrophic equilibrium. Okay, so next. And to develop such schemes, we first rewrite the study system into a vector form ut plus gy is s. Here, u is a vector, includes the conservative variables, and g is our flux function, and s is the source term. And we derive the Goodenough type finite volume methods. We do the space and the time integration over the control volume, and we will obtain the following semi-discrete system. Here, U bar k is the cell average, is the average of the space integration, and the gk plus half is the numerical flux. It's the average of the time integration, and S bar k is the approximation of the source term. So from this system, we can know that if we, at some time level t, if we can know the numerical flux gk plus half, then we can solve this system and obtain the numerical solutions. So now our problem is how to obtain this numerical flux. And from the definition of this numerical flux, we can find that it depends on the flux function. However, this flux function is the global ones because it depends on a global variable L. So it's hard to design an upwind numerical scheme, and it's hard to solve the NEMA problem to obtain this function. So we tend to use the NEMA problem solver free scheme, the Central-upwind scheme, and it's NEMA problem solver free, and it has many advantages. For example, it's robust, and it can be applied in many other works. So here I directly introduce the Central-upwind numerical flux. It's given by this formula. Here A plus and the minus are the left and the right sided local propagation speeds, and it can be estimated using the Jacobians. And here dk plus half is the built-in anti-diffusion term, and also we have the U star. And from these three equations, we can know that if we want to obtain the numerical flux, we have to know the point values U plus and the U minus at the cell interface. So the new problem is how to obtain the point values U plus and the U minus at the cell interface. So next, we try to use the second order piecewise linear approximation to obtain the point values. It's our U tilde of Y, and it's based on the cell average U bar K and the slopes Uy. So at some time label T, if we have the U bar K, and we can use any difference method to obtain the slopes. However, if we directly perform this reconstruction, we cannot need a well-balanced scheme because our static data is P is 0 and the L is constant. We reconstruct the H, we cannot guarantee L is a constant. So instead of the reconstruct the conservative variables U, and to be well balanced, we reconstruct the equilibrium variable V, and also V has the same formula. V bar K is the cell average, and in this V, we just have a new variable L, and from the definition of L, we can compute in this way. Okay, so next we should compute the slopes Vy at the points K, and we can use any method to compute these slopes. For example, the left and the right differences or the central differences. But in this work, in our work, in order to reduce the oscillation of the reconstruction, we just use a linear limiter to compute these slopes Vy. So once we have the reconstruction, we can compute the point values V plus and V minus here. And if we have the V plus and the V minus, it means that we have the QP LB plus and minus at the cell interface. So we will have the, but to compute the numerical flux, we should have the point values H at the cell interface. So now how to compute the H? And arising from the definition of the global variable L, and we have the following cubic equations. So we just need to solve these equations, then we can obtain the point values H. So it means that now we have all the quantities we need to compute the numerical flux. And as mentioned before, if we have the numerical flux, then we can solve the semi-discrete system. Then we can obtain the numerical solutions at each time step. But keep in mind that our goal is to make our numerical schemes to be well balanced. So now we check that whether our schemes are well balanced or not. We record the static data is P is equal to 0 and L is constant. And then we will observe that in the second and the fourth component of the numerical flux, if P is 0 and the least term vanish and the least term vanish, P is 0. But we don't know what's the value of Q and the HB. So it means that these two terms will not vanish. So it indicates that our numerical scheme is not the well-balanced one. So we want to enforce our scheme as a well-balanced scheme. So we introduce a diffusion switch function, h of psi. And in this figure, we plot the profile of the switch function h. And from this figure, we can see that if phi psi is very small, then it means that h is 0. It means that the switch is off. And then if precise than 0 or it's a little large, then the switch is on. So we just need to add this switch into the second and the fourth components. So if we are at the steady state or near the steady state, then we switch off this term and this term. If we are away from the steady state, then we switch on this term and this term. So it makes our numerical scheme is a well-balanced one. Okay, and here I would like to point out two spatial techniques in the implementation of our numerical scheme. The first one is the singularization technique. In the implementation, we should compute the velocity v, which is equal to p over h. But if h is very small, then the computation will be not very accurate. So to avoid this, we should take this technique. And the second one, we know that the h is non-negative and the buoyancy b is non-negative. So in the implementation, we should preserve the positivity. So we just use the join time step technique, and the details can be found in our references. So until now, we have the well-balanced numerical scheme, and then we just need to choose an appropriate ODE solver. For example, here we use this Langue solver, and we choose the time step according to the CF condition. Then we can solve the above semi-discrete system and obtain the numerical solutions. So next, I want to show you some numerical examples. The first one is the template over non-flat bottom topography. And in the left figure, we can see that the bottom topography is non-flat. There are two humps in the bottom topography. And we plot the water surface, which is equal to the water depth plus the bottom topography. And from this figure, we can know that our scheme can preserve the positivity of h, because here and here h is really small, but it's still positive. And also we can find that our method can cope well with the bottom topography. And in the right hand side, we plot the profile of b, and we can see that our numerical scheme can capture the sharp fronts of the temperature b, or temperature gradients of b. And the second example, we study the breakdown phenomena of the small solutions. Under some spatial conditions, if the wave propagation will break down in finite time, so our numerical scheme should have this property to capture the breakdown. And we consider the initial conditions. Here, v is not 0. It's added by a small perturbation. Like this, initially add a small hump. And we wish that this hump will split two parts and propagate to the left and right, and then break down. So now we look at the evolution of this v. At this time, we can clearly see that it splits two parts. One propagate to the left, and the other one should propagate to the right. And at this time, we can see that the right going parts and break down, and then they keep going, and then the left going part also break down here. So this example shows that our numerical scheme has the property to capture the breakdown very well. And the last example is we study the inertial instability. We consider on the equatorial beta plane, and if the vortex is strong enough, then there should exist the inertial instability. Here we consider the initial data like this, and we can check that it satisfies the steady state solutions perfect. So it means that the vortex should remain stationary because there is no perturbation is added. But because there is the discretization method, the error is inevitable. So the discretization error will project onto the unstable mode, and it will keep growing like this. The discretization error is keep growing and localized around 0. So it means that our scheme can capture the inertial instability. Okay, some short conclusions. In this talk, I show you we construct and test a well-balanced scheme for the one-dimensional thermal shear water equations, and this method and this model are much more realistic because we incorporated the non-freighted bottom topography, and we also consider the horizontal density or temperature gradients. And there are some key references. Okay, thank you.
Thank you very much for the talk. Well, I guess it takes some time to digest this talk, so I suggest we move on to the next one. Thank you very much again.